Welcome back to our series of lectures on the topic electromagnetic spectrum, absorption spectra. In this topic so far, we have talked about UV visible spectroscopy, and today we will continue our discussion on the same, and today we will take up Woodman-Fisher rules, and that we will talk about in the context of dye-ins. The session is planned as follows, that is, typically as we have been doing so far, that is, we will try to make a brief review of what we have done in the previous sessions. Thereafter, we will once again revisit the factors which affect UV visible spectrum, because that is what is important for us to build a case for the rules I am going to talk about. Thereafter, we will come down to the Woodman-Fisher rules for dye-ins, and since I am talking about dye-ins, I will try to find what is the basis for these rules for these kind of molecules. Having done that, we will state what are the rules, and then we will try to apply it to a number of systems which are acyclic and cyclic dye-ins, and towards the end we will try to sum up what we do in today's session. Okay. So, let us make a beginning by recalling what we have done so far. What we have done so far in this series of lectures is that we started by explaining the origin of UV visible spectrum and outlined its significance, how is it important there. Thereafter, we outlined and explained the characteristics of UV visible spectrum, that is, if we have a spectrum, what are the characteristics of that, the intensity, the width, the location, and the position of the band, and so on and so forth. Thereafter, we discussed what are the factors which affect UV visible spectrum. Having done that, we moved on to it is a kind of a continuation of these factors. We brought in the concept of color and related it to the conjugation in the molecules, because that is a very important correlation we could establish in one of the sessions earlier. Thereafter, we took up the principle of spectrophotometer, that is, what is spectrophotometer, because to make a measurement we need a device, that is called as a spectrophotometer. So, we talked about the principle of spectrophotometer and described different types of spectrophotometers. Thereafter, towards the end, we explained what is the principle of UV visible spectrophotometry, that is, how do I apply this UV visible spectrum to different kind of applications there. So, that is all what we have done so far. Now, to come to today's session, what we do is to talk about the Woodman-Fisher rules. We will first try to quickly revisit, because these rules basically are related to the effect of different factors, the structural components of a molecule on the UV visible spectrum. So, let us try to recall for ourselves that what are the factors which affect the UV visible spectrum. The first and foremost of the three factors what we have is called as conjugation. We know that the conjugation in the molecule, it affects the position of the absorption band there, and we rationalize in terms of the following example there. We have ethylene here. So, these are the two molecular orbitals for that, and the transition for this is observed at a wavelength about 171 nanometer. But when you go to from ethylene to butadiene to hexatriene, we find that as you move, if you go on extending the conjugation, we find that the molecular orbitals are such that the transition which actually occurs in the what is observed in the UV visible is from the HOMO to LUMO. So, that actually gets of lower and lower energy. As a consequence, the lambda max increases. So, typically what we established in the previous session was that because of conjugation, there is a lambda max increase in the spectrum there. That is one factor which typically affects the UV visible spectrum. And then second thing is the substituents, because in the molecule there are number of substituents are there on the main chromophore. So, these substituents affect in variety of ways. One of the most common ways of substitution affecting the absorption spectrum is, say, hyperconjugation. This is an example which shows this is my basic chromophore, the ethylene here. Suppose you got a methyl substituent here. So, this methyl substituent can undergo hyperconjugation, and as a consequence of that, this makes some slight variation in the lambda max position of the band what we are observing in the molecule there. This effect is much more milder as compared to conjugation. Conjugation is a very significant effect, whereas this effect of substituents is there, is not insignificant, but it is not as strong as that of conjugation. Then the third factor what we talked about was the solvent. Actually, the solvent also affects, because when you run the spectrum, you run in different solvents over there. So, typically we use, depending on the solubility of the molecule, you use ethanol, methanol, or other kind of solvents there. Most of the spectra are done in these alcoholic systems, but in case the molecule is done in some other system, so we have to see that depending on the nature of the solvent, the lambda max will shift there. And what you find is typically the solvent affects by kind of interacting with the molecular orbitals of the molecule, whether they stabilize or destabilize the molecular orbitals. As a consequence, the delta E value changes, and as a consequence what you find is the lambda max shifts. And more often than not, it is the polar solvents which affect the spectrum more significantly, and also that depends on the type of transition also. That means a polar solvent will affect N to pi star transition differently than pi to pi star, and so on and so forth. All that we have discussed in the previous sessions there. Okay. Now, what is important here is that all these effects, that means suppose you have got a basic chromophore there, and to this chromophore there is some kind of conjugation coming there, solvent is there or substituents are there. So, all these effects we just discussed about, they basically all are additive, and that is basically the rationale behind this Woodward-Fisher rules there. So, what we can do is that this contribution can be empirically compiled for different class of organic compounds, and these are called as Woodward-Fisher rules. That means, what we do is we take different class of compounds there. For each class of compound, we try to see what is the basic chromophore there, what is the lambda max for that, and then we see that if you got different kind of contributors which affect this lambda max, so what are the contributors and what are their effects over there. So, all this can be empirically compiled. Basically, what is done is you take the spectra of wide variety of molecules and try to find correlations between them, and then this kind of tableau things can be made use of to predict the lambda max for a given organic compound in terms of all these factors over there. And then we find is that the agreement between the values which are calculated using these rules and what is observed experimentally, they happen to be very good agreement between the two. So, that is basically the rationale for using this kind of Woodward-Fisher rules over there. It is an empirical set of rules there. Now, let us move on to the dienes per se, and what is the basis for these dienes is, that is we know that the simplest to talk about diene, we start with an ethylene chromophore, the basic chromophore there, and for ethylene chromophore there are two molecular orbitals, say pi 1 to pi 2, and the transition between them, as I mentioned earlier, is observed at about 171 nanometer, and this basically is a typical pi to pi star transition, but since it is observed at 171 nanometer, typically we do not observe it because it is in a range beyond what typically is measured for UV visible spectrum there. Okay. Now, if I go to diene now, if I look at diene, let me take the simplest possible diene is the butadiene. If I look at butadiene, so there are 4 carbon atoms there and there are 4 molecular orbitals there, and in this case the transition what you observe in the UV visible spectrum is from pi 2 to pi 3, and that is actually at 217 nanometer. So, what you find is that this pi to pi transition is observed at 217 nanometer, which is in the UV visible range, and that is what we conclude from here is, that is we need a minimum of 2 conjugated double bonds to observe any spectrum in the UV visible range there. That is for the dienes per se. Okay. Another thing what we see is that this butadiene, the simplest possible diene we have, the pi to pi transition which is observed for butadiene at 270 nanometer, it is very sensitive to the substituents there. Let us take some examples there. You see that this is my simple chromophore there, butadiene. Suppose you got a methyl substituent over there, we find it is coming at 220 nanometers, this one is coming at 223, this is at 226, and so on and so forth. That means, if you take the basic chromophore and put different kind of substituents at different locations, we find that lambda max shifts. That is that basically is one of the basis for our Woodward-Fisher rules for dienes. Now, these rules actually, as I mentioned earlier also, was proposed by Woodward and Fisher because they studied the UV spectra of wide variety of terpenes and steroidal molecules containing this kind of chromophore. And this basically the rules go as follows, that is they allocate some base values for different kind of conjugated dienes. Typically what you have is, we have got acyclic diene, that is butadiene, for that the base value is 270 nanometers as we know it. But suppose we got a heteronuclear system there, that means you have a diene which is a part of 2 cyclic systems over there, the base value for this is 214 nanometer, and if it happens to be a homonuclear system, it is 253 nanometers there. So, that is the base value, what has been typically empirically worked out from the basis of the spectra of different kind of molecules studied over there. Then the next aspect is that what is the contribution of the substituents there. So, this is the following table over there which lists different kind of substituents over there and their contribution. What we see is that if you got an extended conjugation, the contribution is very significant, as I mentioned earlier, is about 30 nanometers there. Suppose you got an exocyclic carbon-carbon double bond, it is about +5. Alkyl group or a ring residue, we got 5 nanometer again. OCOCH3 is there is no contribution to that, OR and so on and so forth. So, what you find is that different substituents affect differently, and also what you find is for such a molecule, for a diene, typically the lambda max position will be the base value, which is 217 in this case, and summation, that is sigma, contribution from all the substituents over there. Suppose a given molecule has the basic chromophore and there are different substituents over there. So, we add the contribution of each one of them to the base value to predict the value of for the given molecule there. And of course, we have to have contribution from the solvents over there. Incidentally, for dienes, the solvents do not affect significantly. So, we can ignore the effect of solvent there. So, primarily for dienes there are only two things, one is the base value and second happens to be the contribution from the substituents there. Okay. Now, let us try to go further and see, let us understand, because in this table we saw there is something called as alkyl substituents, something called as ring residues, conjugation we understand, and then exocyclic double bond. Let us learn these terms there. So, let us take some examples there. So, this is one simple molecule here, which is the diene here. In this case, this is my basic chromophore there, which is butadiene, and we find that this is one substituent there, this is another one there. So, these are the two substituents there and they are called as alkyl substituents. Similarly, in this molecule we got the basic chromophore and then we got 3 alkyl substituents there. In this molecule the basic chromophore is this and there are set of 4 alkyl substituents. So, that means what you have to see here is that we have a basic chromophore and any substitution on that basic chromophore, say from carbon atom number 1 to 4, anywhere the alkyl substitution is there, that is the alkyl substituent and that is contribute about +5 nanometers to the lambda max value. Okay. Let us go further, let us look at this molecule. In this molecule what you have is, this is the basic chromophore and now we got 2 substituents here. Now, these 2 substituents here which have been shown here, they actually form a part of a ring there. So, they are called as ring residues. Incidentally, even the ring residues also contribute the same +5 units, but we must distinguish between what is an alkyl substituent and what is a ring residue here. Now, let us take another example here. So, in this case this is a basic chromophore and in this case what you have is we have got 3 ring residues there, because there are 3 on this chromophore here, this is one, this is the second one, this is the third one. So, these are 3 ring residues here. In this molecule what you have, this is my basic chromophore here and what you find is there are 2 kinds of substitutions here. So, in this blue enclosure here, these are 3 ring residues here and this one happens to be an alkyl substituent here. So, in this case there are 3 ring residues and there is one alkyl substituent there. So, one has to be clear about these terms to apply these rules over there. Let us move further and see what do we understand by endocyclic and exocyclic double bonds there. Look at this molecule. In this molecule what you have is, this is a double bond which is a part of the ring system here. So, this is called as an endocyclic because it is inside the ring there. So, this is an endocyclic double bond there, whereas this double bond here is an exocyclic. That means, the double bond happens to be outside exo to the cyclic system there. Okay. Look at this one. In this case this is an endocyclic to this ring here and exocyclic to this ring there. So, that means, this double bond actually is endocyclic as well as exocyclic, because it is endocyclic in this ring, exocyclic to this ring, whereas this double bond actually is endocyclic only to this ring there. Now, let us move further and look at one more example here. In this case what do we have? What do we have is, we have got 2 kind of double bonds there and both of them happen to be exocyclic. This one is exocyclic to this ring and this one is exocyclic to this ring. So, in this case there are 2 exocyclic double bonds and we know that each exocyclic double bond contributes about 5 units to the lambda max value. In this case what do we have? This is very interesting. In this case this double bond is very interesting here, because this double bond actually is exocyclic to this ring as well as to this ring here. So, in this case this will contribute twice as much that means it will be equivalent to 2 exocyclic double bonds, that means it will contribute about plus 10 units to the lambda max value there. Now, let us go further, and one more thing we have to clarify ourselves, that what are these acyclic, homoannular and heteroannular ring system over there. Now, this we know is alicyclic straight chain, this we know is homoannular, because in this case, because the whole chromophore, that means 2 double bonds happen to be part of the same ring over there. This is heteroannular, this also is understandable. But what about this one? What system is this? Is it alicyclic, homoannular or heteroannular? There is a ring though, but in this case this whole chromophore is not part of the ring. So, this is an alicyclic system there. So, in this case why I am talking about this is because these different systems have got different base values. So, if this is my basic chromophore there, this will be taken as alicyclic one and the base value will be about 217. If it happened to be homoannular or heteroannular, the values would have been different there. Similarly, this one also, though in this case also there is a ring system, but we see that this chromophore here is not part of the ring here. So, this again is alicyclic. In this case also we will take the base value to be 270 nanometer. So, this has to be clear before we take up the examples of seeing that how do we apply these rules to predict the values for lambda max for different kind of dienes there. Let us take these examples now. Now, first example is simplest one, this is isoprene. Now, in this case of isoprene, what you find is the chromophore is, this is my alicyclic diene, the base value is 217 nanometer, and what you find is in this case there is only one alkyl substituent here. So, it will be 1 into 5, that is about 5 nanometers, there is nothing else. So, the calculated delta max value will be sum of the two together, that is 217 plus 5, that makes it 222 nanometer, 222 nanometers, and observed value also happens to be about 220 nanometer. The agreement is reasonably okay. Another example, look at this one, this is 2,3-dimethyl butadiene. In this case again the base value will be 217 nanometer. So, that is my chromophore there, and there are 2 alkyl substituents, one here, one here. So, for the 2 alkyl substituents the contribution will be 2 into 5, that is 10 nanometers, and that makes the total to be 227 nanometers, and we find that the observed value is 226 nanometer. Again the agreement is quite good. So, we can see that how useful these rules are. I am taking very simple molecules, but we can take more complicated molecules also, and we find that agreement happens to be reasonably okay. Now, say for this molecule again we have the base value of 217, because that is my chromophore here, butadiene part here, that is this conjugated diene, and then there is one alkyl substituent here, one over here. So, these two put together will again give me contribution of 10 nanometers, and it will add again to 227 nanometers, and observed value also happens to be 227 nanometers. Again the agreement is excellent. Now, for this system is slightly more involved, that is in this case the basic chromophore again happens to be alicyclic diene, and the base value is 217 nanometer, and there are it is very obvious here, just we can see it that there are 3 alkyl substituents there, 1, 2, 3, and the contribution will be 15 nanometers, which will add to give me 232 nanometer, that is my calculated value or the value which I predict on the basis of these rules, and the observed value happens to be 234 nanometer. Agreement is good. So, basically what I want to convey here is that these rules are reasonably good. That means, for simple molecules they predict the values to be in fair agreement with the experimental values there. Okay. Let us take another example here. Now, in this case what you find is what is the basic chromophore here? Again we got an alicyclic diene here. So, the base value will be 217, and what you have is this is one substituent here. So, that gives me 5 nanometers more, and this bulk of the molecule or this kind of isolated double bond over here, it does not contribute because it does not affect the chromophore anyway, because this is farther from the chromophore. So, you find that there is no contribution of this particular double bond or these substituents on the double bond over there, and the value will be just 222 nanometers, and observed value happens to be 224 nanometer. So, what is important is this example conveys one thing very clearly, that we have to just consider what is the substituent on the basic chromophore. We do not have to bother about the bulk of the molecule over there. It may not contribute anyway to the lambda max value for the basic chromophore there. Okay. Let us move further and take one more example here. Now, in this case, what do we have? What do we have is, again we have got the base value of 270 nanometers, because our chromophore is alicyclic system here. And in this case, as we can see clearly, this is the example we took earlier also, they are the ring residues, because these substituents happen to be part of the ring. So, since there are 2 ring residues, so the contribution will be 2 into 5, about 10 nanometers, and that will give me, but in this case there is one more component here, that is this double bond happens to be exocyclic to this ring here. As a consequence, there will be an additional contribution of about 5 nanometers because of this double bond being exocyclic to a ring. This will add to give me a value of 232 nanometers, and observed value is slightly higher than this 232 nanometer, but the agreement is not way off. Let us move further. Let us take another example. Now, you can do on your own also by seeing so many examples here. Again, the basic chromophore happens to be alicyclic diene here, and the base value is 217. And in this case, what do we have? On the chromophore, we have got 1 ring residue, 2nd ring residue, 3rd ring residue, 4th ring residue. So, there are 4 ring residues on this. So, each one will contribute about 5 nanometers, total contribution will be 20 nanometers, and the observed value can be found out by adding to this the contribution of these 2 double bonds. Both of them happen to be exocyclic double bonds, because this is exocyclic to this ring, this is exocyclic to this ring over there. So, the total comes out to be about 247 nanometer, which is in reasonably good agreement with the experimental value, which happens to be 247. Let us go further, take more examples here. Now, in this case, how do we go? We see that here again I have got the basic chromophore as a diene, but this diene now happens to be part of 2 different rings there. So, the base value will change. This is a heteronuclear diene or heteroannular diene. So, in this case the base value will be 214 nanometers. So, that is one deviation from all the examples we have done so far. And then what do we have is, if I look at this basic chromophore and you find that this is one substituent on this, 1 ring residue, this is 2nd ring residue, this is 3rd ring residue. So, there are 3 ring residues to this. So, that will give me the contribution of about 15 nanometers there, and we have got one alkyl substituent also on this. So, that also will give me a contribution of about 5 nanometers, that will give me 5 more. So, in addition to this, between these 2 double bonds here, we find that this double bond happens to be exocyclic to this ring, whereas this double bond is an endocyclic double bond which does not contribute to the lambda max value. So, these are the possible substituents or the contributors to the lambda max. We find that the calculated value comes out to be about 249 nanometers. Similarly, if we take yet another example, this looks to be a little complicated molecule. What you find is that in this case also our kind of estimation of lambda max value is very straightforward, very simple, because we have to first locate what is our basic chromophore. The chromophore happens to be this diene here. Now, this diene happens to be part of this given ring here. So, this is a different kind of base system there. So, in this case the base value for this homoannular diene is 253 nanometers. So, this value is going to be different from the previous examples again. And what more is there in this case? What more there in this case is that on this basic chromophore, if you look, this is 1 ring residue, this is 2nd ring residue on this, this is 3rd ring residue, this is the 4th ring residue. So, there are 4 ring residues to this. So, each will contribute about 5 nanometers, that makes it 20 nanometers. What more is there? What more is there is that we got this double bond is exocyclic to this ring, this double bond is exocyclic to this ring. So, there are 2 double bonds, both of them are exocyclic. So, they will contribute 5 nanometers each, the contribution will be 10 nanometers, and the value will be coming out to be about 283 nanometers, and the observed value happens to be 282 nanometer. Agreement is excellent over there. Let me take some more examples here to establish the applicability of these rules. Now, if you look at this molecule hexatriene, I will come back to alicyclic system again. I have been talked about two other kind of base values there. Now, in case of hexatriene, what do we have? The basic chromophore we can pick from here. This is my butadiene, or I can take this as my basic diene here, and the base value will be 270 nanometer. And in this case, suppose I take this to be my basic chromophore there, we find that there is an extension of conjugation here. This double bond is conjugated with this particular chromophore there. So, they will contribute about 30 nanometers to this. And in addition to that, there is no substitution now, because this is my basic chromophore and this is extending a double bond over there. So, the chromophore now becomes this whole system and there is no substitution, nothing else. So, the value will come out to be 247 nanometer, and observed value is close to that one, but not exactly 247. Let us move further. Let us move further and look at this molecule. In this case, we have got the basic chromophore. You can start from this side or somewhere here. We can go any which way, it will come to be the same. What you find is the base value is 270 nanometer, because it is an alicyclic diene. And what do we have here is, okay, let me assume that this is my base chromophore here, and then this is my extension of conjugation. So, this will give me a contribution of 30 nanometers. Then what do we have is, now since my chromophore now becomes from here to like this, so this is one alkyl substitution here, which will contribute 5 nanometers. We find that we have got one more substitution here, that is O-methyl at this position. And if you look at the tables as I showed you earlier, the O-methyl, that is O-alkyl group, give a contribution of about 6 nanometers there. So, that adds to give me a value of about 258 nanometers for this particular system there. Let us move further. Let us move further and take some more examples here. Now, in this case, there are possibilities of two base values here. If I look at this as my chromophore, this is heteroannular. If I look at this one, this happens to be homoannular. So, in this case, we give precedence to the homoannular system here. So, in this case, the base value will be 253 nanometers, and this double bond essentially will be taken as the conjugation of this basic chromophore there. So, this will contribute 30 nanometers. Our basic chromophore now becomes this homoannular system and this extended conjugation here. So, on this basic chromophore, what do we have is, we got 1, 2, 3. So, there are 3 ring residues, they will contribute 3 into 5, 15 nanometers. In addition to that, what do we have is, we find that this double bond is endocyclic. This is an exocyclic double bond. This also is endocyclic here. So, there is one double bond which is exocyclic. So, that will contribute about 5 nanometers more there. Then what do we have? We have got one more substitution on this particular chromophore here, and incidentally this substituent does not contribute anything, the contribution is 0 nanometer. So, for this system, our predicted value or the calculated value comes out to be about 303 nanometers, and the observed value happens to be 306 nanometers, which is in good agreement again. Now, let us go further and look at this simple molecule here, octatetraene. In this case, this is my basic chromophore. We find that this is one extension of conjugation, this is second extension of conjugation. So, base value 270 nanometers, extension of conjugation 60 nanometers, because there are two groups, that is 2 into 30, that makes it 60 nanometers, and there is no substituent at all. So, this gives me a value of 277 nanometers there, and observed value is 290. Let us take this molecule here. Now, in this molecule, what do we have is, we have got the basic chromophore is the same, then we got 1, 2, 3 extension of conjugation, and the value we can see it will be 217 for the base value, and for extension of conjugation the contribution will be about as much as about 90 nanometers, and that will add to give me value of 307 nanometers, and observed value happens to be 334 nanometer. So, what you find is, as we go on extending the conjugation till hexatriene, it was fine. When we went to octatetraene, we found that the deviation was there, but when I come to decapentaene, I find that the deviation is large. The significance or the outcome of this particular set of examples is that if I go on extending conjugation, then these rules there is a large deviation between the predicted values and the observed values, and in such cases the rules have been modified, and for these kind of molecules we use what are called as Fischer-Kuhn rules. That is, for alicyclic dienes having more than 4 double bonds there, and the rules happen to be as follows. That is, the lambda max can be given by the following expression here. That is, alicyclic dienes having more than 4 double bonds. So, this is the expression here. Well, let us understand what is the meaning of this expression here. This is the base value 114, and then 5 m. M happens to be the number of alkyl or alkyl-like substituents on the conjugate system. So, that is one parameter there, and this n happens to be this n here. N is appearing in two places there, one outside this bracket, one inside here as a multiplier to this factor 1.7 here. Now, this n happens to be the number of conjugate double bonds. That means all double bonds put together, the basic chromophore as well as the conjugate system over there. And then this R endo happens to be the number of rings with endocyclic double bonds in the conjugate system, and R exo happens to be the number of rings with exocyclic double bonds there. Now, these are the Fischer-Kuhn rules there. Let us try to apply these rules to some examples here and see that what kind of agreement we get in this case. Let us look at this very common molecule lycopene, which is the pigment in our the tomatoes. Now, if you look at lycopene, what you find is that this is a large conjugated system here. And if you look at the chromophore, so this may be my basic chromophore, and this all is extension of conjugation here. Mind you, this double bond and this double bond here are not part of the chromophore, because there is a gap of about 2 bonds or 3 bonds over there. So, for conjugation it has to be alternating double bond over there. Okay. So, for this system what do we have? We have got n is equal to 11. That means, if we look at, just count it here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So, there are 11 double bonds which are conjugated. It is inclusive of the base chromophore there. So, n happens to be 11 here. Now, if you look at m, that is, m happens to be the number of alkyl or alkyl-like substituents here. So, if we look at this chromophore, we find that, so from this, if I start from here, this is one substitution here, this is second one, 2, 3, 4, 5, 6, 7, and this is the 8th one here. So, there are 8 substitutions on this, and there is no ring over there. So, R endo and R exo happen to be 0 each. Put into the expression here, lambda max count will be 114, the base value here, 5 m and all these values over there. Substitute into this. So, we find that this is my m is 8 here, I substitute over there and substitute 11 as a value of n here. If I calculate, I find the value comes out to be 476.3 nanometers, and the observed value happens to be 471. The agreement is reasonably good. It is not as way off as was happening in case of octatetraene and decapentaene and so on and so forth. Let us take one more example here, beta carotene. In this case also, it is an extended conjugation system, that is what is there in caret here. Now, in this case, if you just count here, n happens to be 11, m happens to be 10 here, there are more substituents over there. And in addition to this, what you find is that in this chromophore here, this extended system over there, we find that this chromophore happens to be part of ring system there, and in these two rings the double bond happens to be endocyclic here. Okay. So, if I just put these values over there, this is my basic expression here, substitute the values here, we find that there are 10 substituents over there. So, it is 5 into 10, 11 is the number of double bonds there, and this 2 happens to be the endocyclic ring systems over there. So, 16.5 is the contribution of each, and if I solve this expression, I find the value comes out to be 453.3 nanometers, and the observed value happens to be 454. Again, an excellent agreement over there. Then yet another example. So, in this case, what you find is n is 11, m happens to be 9, R endo is 2, R exo is 0. Again, this is my basic expression there. Substitute the values, I find the calculated value comes out to be about 448 nanometers, and the observed value happens to be 452. Quite a good agreement again. So, with this we come to end of this session, and we done not many examples of application of this Woodman-Fisher rules and Fischer-Kuhn rules over there. Now, let us sum up what we have done today. What we have done today is we reviewed the contents of the previous sessions, and then thereafter we revisited, in this context of reviewing, we revisited the factors which affect the UV visible absorption. Then thereafter we came down to the theme of today's session, that happens to be the Woodward-Fisher rules. We explained the basis for these rules and then stated these rules and applied them for variety of alicyclic and cyclic dienes there. And by this application, we kind of predicted the lambda max position for these molecules, and we found that the agreement between the predicted values and the observed values was reasonably good. Now, in next session, we will continue our discussion on Woodward-Fisher rules, and we will try to see that what are the rules for enones kind of systems. That means, there is a conjugation between a ketone and an alkene, enone systems. So, we will see that what are the rules for those systems, and then what kind of agreement is there between the predicted values and the observed values for enones.